Welcome to Chapter 5 on binary representation. Before we begin with the description of binary representation, I need to define what division and modulo are. We're given two integers, a and b. Note that we require that b is strictly positive. Namely, b is greater than 0. It's 1, 2, 3, and so on. Now let me define two functions. Division, this is integer division, and modulo, which computes the remainder when you take division. What is division? Well, when I want to divide a by b, the quotient is the maximum number q. Q is, of course, an integer, such that q times b is less than or equal to a. The remainder, or the modulo of a and b, or sometimes we say a mod b, is defined to be the difference between a and the product of b and the quotient a divided by b. Okay, so we call this number a divided by b the quotient, and we call this number mod of a comma b the remainder. Now, if the remainder is 0, then a is a multiple of b, or we say that a is divisible by b, because you can divide a by b, and the remainder that you get as a result of this division is 0. Sometimes people write a divided by b is the ratio a to b rounded down to the nearest integer. We often denote the remainder of a comma b by a mod b, mod of a comma b, a of mod b, and so on. All these things denote the same thing. This is the remainder when you divide a by b. Let's see a few examples. In the first example, we want to divide 3 by 5, right? The remainder when we divide 3 by 5 is 3, because the quotient is 0, 0 times 5 is less than 3, and 1 times 5 is greater than 3. Therefore, the quotient is 0, and the remainder is 3. If we take 5 divided by 3, the remainder will be 2, because the quotient will be 1, and we will have 5 minus 1 times 3 equals 2. If we take 999 divided by 10, the remainder is 9. 123 divided by 10, the remainder is 3. You notice that in the case of division by 10, if the number is given in decimal representation, then computing the remainder is very easy. It is simply the least significant digit. Here it's a 9, and here it is a 3. Now, what happens when we divide by 2? The remainder of dividing a by 2 equals 1 if a is odd, and 0 if a is even. Okay, we will in a second prove that the remainder is never negative, and that the remainder is strictly less than the number you're dividing by, and therefore it is less than or equal to b minus 1. So the first claim we want to prove is that the remainder, when you divide by b, is a number in the set 0, 1, 2, up to b minus 1. This is the first claim we want to show. Okay. Instead of giving a formal proof, I will give a proof by a picture. So consider here the axis of all the numbers. Here we have 0. Here we have b, 2 times b, 3 times b, and so on. And we also have the negative sides, minus b, minus 2b, and so on. Recall that I assume that b is not negative. Now, the quotient A divided by B is defined to be the maximum Q such that Q times B is less than or equal to A. So what happens is I take two successive multiples of B. The first multiple is A divided by B times B, and the next one is A divided by B times B plus B. So this is one multiple of B, and this is the next multiple of B because I've simply added B to it. Now A falls in this interval. In fact, A falls in the half-closed, half-open interval. Let's emphasize this fact. So A has to be greater than or equal to A divided by B times B and strictly less than A divided by B times B plus B. Okay. So this is the interval we're focusing, and A can be anywhere in this interval. The remainder of A divided by B is denoted here in blue. This is the difference between A and A divided by B times B. Okay? Now, this difference, since A resides in this interval, and this is the left boundary of the interval, this difference is always non-negative. So the remainder cannot be negative. On the other hand, because A is in this open interval on the right-hand side, it cannot reach this point. Therefore, the difference is strictly less than B, and since the difference is an integer, it is less than or equal to B minus 1. So we conclude that the remainder is never negative and that it is always less than the divider. So it is less than or equal to the divider minus 1. Now, as a question, to see if you understand this definition, consider the case that A is negative. For example, A equals minus 11. And the divider is 6, B equals 6. Well, what is going to be this side of the interval? This side of the interval is going to be minus 12. And minus 11 is in fact minus 12 plus 1. So the difference between A, which equals minus 11, and the left-hand side of this interval, which is minus 12, this difference is exactly 1. And therefore, the remainder of dividing minus 11 by 6 is 1. Good. Now, I want to prove the second claim. The second claim says the following. If I can represent A as a multiple of B, Q times B, plus R, where R happens to be an integer between 0 and B minus 1, then in fact Q is the quotient of A divided by B, and R is the remainder, A mod B. That means that there's a unique way of performing division. That's why I say division and modulo are well defined. If I want to define A by B, there's only one quotient and one remainder that I can assign to this operation of division, because whenever I can write A equals Q times B plus R, this Q will be the quotient and this R will be the remainder. Of course, this is provided that R is between 0 and B minus 1. So let's prove this claim, this fact that division and modulo are well defined. Okay. So, suppose that we have two ways of representing A. The first one is Q1 plus B plus R1, and the second one is Q2 times B plus R2, where in both cases, these addends, R1 and R2, are between 0 and B minus 1. Notice that this is an open interval, so R1 and R2 are strictly less than B. Well, I claim that if I have two such representations of A, then these pairs are equal. Q1 equals Q2 and R1 equals R2. How do I show that? Well, without loss of generality, I can assume that R2 is greater than or equal to R1. If this is not the case, then I just flip them. Good. Now I subtract these two equalities. This minus this, and all of them equal a. So I get on the left-hand side, I get 0. And on the right-hand side, excuse me, I get the difference. The difference, Q2 times B minus Q1 times B plus R2 minus R1. And because I assume that R2 is greater than or equal to R1, the difference R2 minus R1 is not negative. And of course, it's not greater than R2, and R2 is less than B, so this difference is also less than B. Great. Now let's look at this equation. 0 equals Q2 minus Q1 times B plus R2 minus R1. 0 is divisible by B, right? The remainder when you divide 0 by B is 0. Q2 minus Q1 times B is also divisible by B. The quotient is Q2 minus Q1, and the remainder would be 0. This means that R2 minus R1 is also divisible by B. What does it mean that it's divisible by B? I know that this difference, R2 minus R1, is a number in the set 0, 1, 2, 3, up to B minus 1. But the only number in this interval which is divisible by B, because this interval does not include B, is 0. So I conclude that R2 minus R1 is 0. This means that R1 equals R2. But if R1 equals R2, then Q1 has to equal Q2, and that completes the proof. Okay, so we have concluded that the remainder is always between 0 and B minus 1, where B is the divider, and that there is a unique way of representing A as a quotient times B plus a remainder, where the remainder is between 0 and B minus 1. The next lemma we want to prove is that if you take x and add to it a multiple of b, z times b, then the remainder that you get when dividing x by b equals the remainder that you get when you divide x plus z times b by b. Let's prove this lemma. It's an easy lemma. Okay, so let Q denote the quotient, A divided by B. Let R denote the remainder, A mod B. That means, according to the previous lemma we have, that A equals Q times B plus R, where R is, of course, between 0 and B minus 1. Now, let's add Z times B to A. So A plus Z times B is simply QB plus R, because A equals QB plus R, plus Z times B. This is the Z times B we're adding. Now let's rearrange things. We get that A plus Z times B equals Q plus Z times B plus R. Now this is a representation of A plus Z times B as a multiple of B plus a remainder, where the remainder is between 0 and B minus 1. By the previous claim on the uniqueness of the quotient and the remainder, we conclude that the quotient of A plus ZB divided by B is Q plus Z. This is this quotient. And that the remainder of A plus ZB when you divide by B is R. This is what you have over here. Hence, we conclude A mod B is R, but also A plus ZB mod B also gives you R, and that completes the claim. The second lemma that we want to prove says as follows. Assume we want to compute the remainder of x plus y when you divide it by b. Now what you could do is you could take the remainder of x when you divide by b. You could take the remainder of y when you divide by b. You could add them, add these remainders, and then look at the remainder that you get when you divide the sum of these remainders by b. And the lemma says that these two numbers are equal. Let's prove this lemma. Sorry. Good. Let's take x and y, divide them by b. These are the expressions you have over here and over here. You get that x equals qxb plus rx, and y equals qy, this should be a y, sorry. Qyb times b plus ry, where both remainders rx and ry are between 0 and b minus 1. Now, let's add x and y together. This is what we wanted to prove, right? We take x and y, we add them together. X plus y, we take these two equalities and we add them. Qx plus qy times b plus rx plus ry. By the previous claim, where you substitute z equals qx plus qy, which is the multiple of b by which you add, you get that the remainder of x plus y mod b equals the remainder of rx plus ry mod b, because you're adding here a multiple of b. And this is exactly what we needed to prove, because this thing, because this part is rx and this part is ry. And that completes the proof. Having defined division and modulo, let's recall what a binary string is. A binary string is just a finite sequence of bits. We have different ways of denoting binary strings. As a sequence, I goes from 0 to n minus 1. As a vector with coordinates 0 to n minus 1. As a vector denoted here by an arrow, if the indices are known and you don't really need to specify them. And we often denote AI by A sub I. All these things are the same. That's a binary string. Now, when we write A from 0 to 3 equals 1, 1, 0, 0, this is a shorthand that means A0 is 1, this is A0. The next bit, A1 is 1, this is A1. The next bit, A2 is 0, this is A2. The next bit, A3 is 0, this is this bit. This notation is zero-based. The indices start at 0, and therefore, when you talk about the third bit of A, it's actually indexed by 2. Okay? So here you see an example. A from 3 to 0 has the positions 0, 1, 2, 3, and the contents are 1 in position with the position with index 3, 1 in the position with index 2, and so on. Now, one thing we can do with strings is that we can concatenate them. So suppose I have two strings. Here is A and here is B. A has bits from position 0 to position n minus 1. B has bits from position 0 to position m minus 1. Now what I do is I define a new string, C. What I do in C is the indices of C go from 0 to n minus 1 to n plus 1 up to n plus m minus 1. This is the sum of the length of B and A equal the length of C. Now what I do is I copy the bits of A into the corresponding positions in C, and I copy the bits of B in the corresponding positions of C to obtain a new string C whose length is the sum of the lengths of A and B. So formally speaking, CI equals AI if I is between 0 and n minus 1, and it equals B of I minus n if I is greater than or equal to n and less than n plus m. This is exactly what we see here in the depiction. We denote the operation of concatenation by this small circle. We already used the small circle to denote something. This was this was composition of functions. Now we're using the same symbol, don't be confused, to denote concatenation of strings. So C is the concatenation of A and B, means what you see here in the diagram. Some examples of concatenation. Let A be the string 1, 1, 1. Let B be the string 0, 1. Let C be the string 1, 0. So when I concatenate A with B, I write here 1, 1, 1. I write here 0, 1 for B, and I get the new string 1, 1, 1, 0, 1, and so on. Now, one very confusing issue, which often occurs in the representation of binary strings, is how do we write the binary strings? Do we start with the high index and go to the low index, or vice versa? So suppose we have here I less than or equal to j. Do we write A from I to j or A from j to I? And this is indeed a very, very confusing issue. The notation that we use is that both these vectors or strings denote the same sequence. It's AK from k equals I to j. When we write AI colon j as a string, the leftmost bit is AI and the rightmost bit is AJ. On the other hand, when we write AJI, the leftmost bit is AJ and the rightmost bit is AI. This is an incredibly confusing issue, and it is known in the nomenclature of computers as big endian versus little endian. So, as I said, in this example, we see two ways of representing the same string A that has 4 bits. When we write A from 3 to 0 equals 1, 1, 0, 0, we mean that A3 and A2 are equal 1, and A1 and A0 equal 0. But if we were to write A from 0 to 3 equals 1, 1, 0, 0, that would mean that A3 and A2 are 0, and A1 and A0 are 1. So there is place here for confusion, and you have to get used to it. Okay. The least significant bit of the string Aij is the bit Ak, where k is the minimum between I and j. And the most significant bit of the string Aij is the bit Al, where L equals the maximum of I and j. And we abbreviate LSB for least significant bit and MSB for most significant bit. So here we have two examples. A from 0 to 4. We have the indices 0, 1, 2, 3, 4. This is the least significant bit, and this is the most significant bit. Here I wrote B from 3 to 0. The indices are 0, 1, 2, 3. So this is the most significant bit, and here the 0th position is the least significant bit. So it is not true that the least significant bit is always on one side of the string. It depends on how the indices are ordered. Okay, some examples. If I write A03 equals 1100, then the least significant bit is A0 equals 1. So A0 equals 1. The most significant bit is A3. A3 here equals 0. So we write the most significant bit is 3. If I take the least significant bit of A from 3 to 0, it is A0, and it will be 0. And the most significant of A is A3, and here A3 is the 1. So you notice I reversed here the order of the indices. Here they went from 0 to 3. Here they went from 3 to 0. I kept the same string, but in fact what I did was I reversed the string. So what was A0 over here became A3 over here, and so on. I want to emphasize, it's not the case that the least significant bit is always on the left side, okay? It depends on how you decide to write the strings. Good. Now we are ready to define how numbers are represented by binary strings. This is called the binary representation. So consider a natural number A, And we say that A is represented by the string capital A, whose bits go from position 0 to position n minus 1. And this number A is represented by the string will be the sum of this series. The sum goes from I equals 0 to n minus 1. These are the bits of A. I take the ith bit of A and I multiply it by 2 to the I. So in fact, the bits A0, A1 up to an minus 1 are coefficients of a power series with respect to powers of 2. 2 to the power of 0, 2 to the power of 1, up to 2 to the power of n minus 1. Now, notice that when we do this summation, we multiply by a power of 2. Sometimes we refer to this power of 2 as the weight of AI. So in binary representation, every bit has a weight, and the weight that is associated with bit AI is 2 to the I. And when we add the weighted values of the bits, we get the number which is represented by the binary string. Okay. We use the following notation. Given a binary string A, we use these triangular brackets to denote the number that is represented by the binary string A in binary representation. And this number is defined to be the sum of the power series AI times 2 to the I, where I goes from 0 to n minus 1. Okay. To simplify things, we will denote binary strings by capital letters and numbers by lowercase letters. Let's see some examples. Consider the string A from 2 to 0 consists of 3 bits, 0, 0, 0. What is the number that is represented by A in binary representation? Well, we expand the series, the power series. We substitute A0, we write 0, A1, we write 0, A2, we write 0, because A2 to 0 is 0, 0, 0. So we plug in the zeros over here. The summation of these zeros is simply 0. Let's look at B. B from 3 to 0 is 0, 0, 0, 1. This means that the 1 corresponds to B0 and all the rest of the bits of B are zeros. So the value, that is the number that is represented by B in binary representation, is this power series. We replace B0 by 1 because B0 is 1 and all the other bits of B are zeros. We add this power series, we get 1. C from 3 to 0 is 1, 0, 0, 0. This means that C3 is 1 and all the rest of the bits of C are 0. So now when we want to know what is the number that is represented by C in binary representation, we write this power series and we do the substitution. C0 is 0, C1 is 0, C2 is 0, C3 is 1. We add this power series and we get that the number that is represented by C in binary representation is 8. Okay. Consider the following situation. I have a binary string A, and I extend A by leading zeros. What does that mean? I concatenate zeros in indices that are higher than n minus 1. Namely, I extend the length of A, that has n bits, to m bits, where m is greater than n, and I define the new bits, ai, for I from m minus 1 to n, to be equal to 0. So here's a depiction. I started with the string A. The bit positions were from 0 to n minus 1. And I end up with a new string that has A in the beginning and continues with zeros up to position m minus 1. Okay? This string is called the extension of A by leading zeros. Okay, let's see an example. A could be the string 1, 1, 1. B could be the string 0, 0. Now we concatenate B with A to obtain the string 0, 0, 1, 1, 1. So we wrote the zeros in positions which are higher than the positions of the bits of A. Therefore, they're called leading zeros. Okay. What happens when we perform concatenation? Consider the following example. I have the string D, that is 1, 1, 0, 0, and I extend it by 3 leading zeros, 0, 0, 0. So now I can ask, what is the number that is represented by C in binary representation? What is the number that is represented by D in binary representation? And in both cases, the strings represent the number 12. Namely, the fact that I wrote here the zeros to the left, and the left I mean in higher indices, because you can see that as I go here to the left, I'm increasing the indices. So, as I added leading zeros, I did not affect the value that is represented by the string. And this is exactly what the lemma states. It says if m is greater than n, and the bits of A in positions n to m minus 1 are all zeros, then the binary number that is represented in binary representation by the string A from position m minus 1 to position 0 equals the number that is represented by the string A from position n minus 1 to position 0 in binary representation. Let's prove this claim. Okay, so we're concatenating the all zeros string, and we want to claim that that does not affect the value that is represented by the binary string. Okay, so we take the number that is represented by A in positions m minus 1 to 0. By definition, this is the sum of the power series. Now we take this power series and we partition the range to 0 to n minus 1 and n to m. What do we know about the bits in this range between n and, this should be m minus 1, I'm sorry. What do we know about the bits in position n to m minus 1? We know that they're all zeros. So this whole power series becomes 0. What do we know about this sum? Well, this sum is exactly the number that is represented by A from position n minus 1 to 0, by definition. And that concludes the proof. Okay. Suppose I have a binary string that consists of k bits from position 0 to position k minus 1. What can I say about the number that is represented by the binary string A in binary representation? I claim that this number is not negative and is less than or equal to 2 to the k minus 1. Before we prove this lemma, let's try to see what is the largest number that you can represent using 8 bits. Well, if you have 8 bits, k becomes 8. 2 to the k is, 2 to the 8 is 256. So you could represent numbers from 0 to 255. If k were 10, then 2 to the k, 2 to the 10 is 1024. That means that you could represent numbers from 0 to 1023. Let's jump to the case where k equals 32. If k equals 32, then 2 to the 32 is 4 gigabits, which is roughly 4 billion, 4.29 billion. Okay? So with 32 bits, you can represent numbers from 0 to roughly 4 billion. What happens with 64 bits? Well, with 64 bits, you can represent numbers which are roughly up to 1.8 times 10 to the power of 19. Now, what I want to emphasize is that, in fact, we can learn something from this discussion. And the thing that we can understand now is perhaps why modern architectures use 64 bits per string rather than 32 bits. These are called 64-bit architectures. Why is that the case? Well, because the minute you have a disk whose size is bigger than 4 gigabit words, 4 gigabit bytes, then you have a problem that you cannot address directly a block in your disk using 32 bits. You need more bits. And this is why the size of the word in computer architectures has been increased from 32 to 64, simply because the disks became too large to be addressable by 32 bits. Okay, so now we want to prove this lemma. The first part, that the number that is represented by a binary string is never negative, is easy, follows from the definition directly. Let's now provide this upper bound. Okay, so the number that is represented by A is this power series. Now, every coefficient over here is either a 0 or a 1. Therefore, this summation is less than or equal to the same summation where I replace each AI by 1. Now, what do I get when I look at this power series? This is a geometric series whose sum equals 2 to the k minus 1 divided by 2 minus 1, because the ratio of this geometric series is 2. Good. And this completes the proof. We now want to address the following problem. Suppose I have a fixed budget of k bits. This is the length of the binary strings that I'm willing to have. And now I want to deal with two questions. First question is, how do I compute the binary representation of a natural number using a string that has k bits? And the second question I have is, can I prove that there is a unique binary representation that uses k bits to every number in the range between 0 and 2 to the k minus 1? Let me discuss for a second why these two goals are of interest. Consider a line in your programming language where you assign x the value 13. But now you know that computers work with zeros and ones, so that computer will have to represent 13 in binary representation. It will have to turn it into a string such that that string represents 13 in binary representation. So that would be the first reason why you would like to know how to compute the binary representation of numbers. The second issue that deals with uniqueness of representation is important because of the following situation. Suppose you write an if statement that compares the value of x and y, and if the values that are represented by x and y are equal, then you do something. Now, one way of comparing the values of x and y is to take the binary strings that represent x and y and compare them bit by bit. If all the bits are identical, then clearly they represent the same number. But is it possible that these two binary strings are different and yet they represent the same number? Well, this cannot happen if every natural number has a unique binary representation, because then you would know that there could not be two different representations for the same value, and in order to compare the values, it suffices to compare their representations. Okay, let's deal with the first problem. I want to present an algorithm, binary representation, that receives two inputs, x and k. X is a natural number, and k is your budget in bits for the length of the string. So now the algorithm outputs a binary string of k bits denoted by a starting from k minus 1 to 0. What should the algorithm satisfy? If x is in the right range, if x is greater than or equal to 0 and strictly less than 2 to the k, then the string that the algorithm outputs should satisfy that it represents x in binary representation. If x is too big, then the algorithm should output fail, because we know that using k bits, you cannot represent a value that is outside of this interval. The algorithm for computing the binary representation of a natural number x using k bits is a recursive algorithm. The base cases for the recursive algorithm are that x is too big or that k equals 1. So if x is greater than or equal to 2 to the power of k, then we immediately know that x does not have a binary representation using a binary string that has k bits, and therefore we can immediately say fail. If k equals 1, that means that x is between 0 and strictly less than 2 to the k, which is 2. So that means that x is either 0 or 1, in which case the binary representation of x using a single bit is x itself. If you want to represent 0, you return 0. If you want to represent 1, you return 1. Good. So these are the stopping cases or the base cases. What is the reduction rule? The reduction rule deals with two cases. Either x is greater than or equal to 2 to the power of k minus 1, or x is less than or equal to 2 to the k minus 1 minus 1. In the first case, what we do is we say the most significant bit of the output will be 1, and the remaining bits are computed by a recursive call to the algorithm binary representation with the parameters x minus 2 to the power of k minus 1 and k minus 1. In the second case, the most significant bit of the output is 0, and the remaining bits are the binary representation of the same x without any change, but using fewer bits. Before I prove the correctness of the algorithm, let me show an execution of the algorithm on two cases. The first case, x equals 2 and k equals 1. Okay, so the stopping condition compares x with 2 to the k. And indeed, x is greater than or equal to 2 to the k, because 2 equals 2, and therefore we declare failure immediately. Indeed, with a single bit, you cannot expect to represent the number 2. With a single bit, you can only represent the number 0 or 1. Now let us consider the case where we want to compute the binary representation of the number 7 using 3 bits. So x equals 7 and k equals 3. Okay, the stopping conditions, let's see if they apply. Is 7 greater than or equal to 3? The answer is no. Does 3 equal 1? The answer is again no. So therefore we go to the reduction rule. We apply the first case. 7 is indeed greater than or equal to 2 to the power of 3 minus 1, which is 2 to the power of 2, which equals 4. So 7 is greater or equal to 4. Therefore, we know that the MSB, the most significant bit, will be 1. And we apply the algorithm recursively with 7 minus 2 to the power of k minus 1. K is 3. K minus 1 is 2. So it's 7 minus 2 to the 2. And k minus 1. K is 3 minus 1. 7 minus 2 to the 2 is 3. 3 minus 1 is 2. So now let us compute the remaining bits of A based on an execution of the binary representation on the number 3 with 2 bits. Again, we check the stopping conditions. Is 3 greater or equal to 2 to the 2? The answer is no. Is 2 does 2 equal 1? The answer is no. So now we go to the reduction rule. We check, is 3 greater than or equal to 2 to the power of 2 minus 1? K minus 1 is 2 minus 1. The answer is yes. So we know that the most significant bit of the remaining part of the answer, that would be A1, is 1. And now we apply the binary representation algorithm recursively, this time with the parameter 3 minus 2 to the power of k minus 1. Our k was 2 in the recursive call, so k minus 1 is 1. And k minus 1 here, the k which equals 2 over here becomes k minus 1 is 1. Good. 3 minus 2 to the power of 1 is just 1, so we execute binary representation of 1, 1. But now the stopping condition holds. And because the stopping condition holds with k equals 1, we just return a0 equals 1. To conclude, we get the binary string 1, 1, 1 as the output, which represents 7 in binary representation. We now want to prove the correctness of the algorithm. Namely, if k is greater or equal to 1 and x is greater than or equal to 0 and strictly less than 2 to the k, then the string which is computed by the algorithm binary representation with parameters x and k represents in binary representation the value x. How do we prove this claim? The proof is by induction on k. The induction basis, when k equals 1, well, in this case, we know that k is either 0 or 1. Sorry, that x is either 0 or 1. Its binary representation is therefore x itself, and this is exactly what the algorithm does, and therefore the algorithm is correct. The induction hypothesis is that the number that is represented by the output of the algorithm for k bits equals x. Now we want to prove the claim for k plus 1 bits. Namely, that the output of the algorithm for x and k plus 1 equals x if x is between 0 and strictly less than 2 to the power of k plus 1. The proof proceeds in two cases. First case is that x is less than 2 to the power of k. If x is less than 2 to the power of k, then the algorithm with parameters x and k plus 1 sets the most significant bit to 0 and applies the algorithm recursively with the same x but with k instead of k plus 1. There's a mistake here. Let me fix it. K. This is k. And this should be also k. Sorry. Good. Now, the induction hypothesis tells us that the algorithm on x and k outputs a binary string that represents x. Therefore, let's see what is the number that is represented by the string that the algorithm outputs for x and k plus 1. The most significant is 0, and the remaining bits are computed by the recursive call. The recursive call, we know that this 0 does not influence the number because this is a leading 0. Okay, so here we're using the fact that a leading 0 does not change the value that a string represents. Now we apply the induction hypothesis. We know that this number equals x, and that completes the first case. Let us prove the second case. In the second case, x is greater than or equal to 2 to the power of k, and of course it's not greater than 2 to the power of k plus 1 because this is the assumption in the induction step. Good. What does the algorithm do when executed on x with k plus 1 bits? It sets the most significant bit to 1 and applies the algorithm recursively with the value x minus 2 to the k and a budget of k bits. The induction hypothesis tells us that this recursive call returns a string that represents x minus 2 to the k. This is the number that is given as a parameter. Why is this? This is true because x minus 2 to the k is less than 2 to the k, and this holds because of the assumption that x is less than 2 to the power of k plus 1. Okay, what do we conclude? That the binary string that the algorithm outputs represents the number which is represented by the string in which the most significant bit is 1 and the remaining bits are computed recursively. Now, this 1 has a weight of 2 to the power of k because it appears after k bits. So its index is k because the bits here have indices from 0 to k minus 1. So this one has weight 2 to the k, and we take the remaining string and look at what is the number that it represents. Well, the remaining string, by the induction hypothesis, represents x minus 2 to the k. So we copy the 2 to the k, and the number which is represented by the recursive call is x minus 2 to the k. The 2 to the k cancel out, and we're left with x, and that completes the proof. The algorithm for computing the binary representation of a number x using k bits is a recursive algorithm. The stopping condition consists of two subcases. In the first case, we check whether x is greater than or equal to 2 to the k. Recall that with k bits you cannot represent numbers this big, and therefore you can announce failure immediately. If k equals 1, then x can only equal 0 or 1, in which case its binary representation is simply x. These are the base cases. The reduction rules compare x with the threshold. The threshold is 2 to the power of k minus 1. If x is greater than or equal to the threshold, then the most significant bit in the binary representation is 1, and we apply the algorithm recursively, not with x minus 2 to the power of k minus 1, because this 1 already contributes 2 to the power of k minus 1 towards the representation of the number, and we're left with a budget of k minus 1 bits. If x is below the threshold, then the most significant bit is set to 0, and then we apply the algorithm recursively with x and with a budget of k minus 1 bits. I want to present an alternative view or interpretation of the binary representation algorithm. Let me denote by bk the set 0, 1, 2 up to 2 to the power of k minus 1. Recall that this is exactly the set of numbers that is representable using k bits in binary representation. Now, we claim that if x is in bk and a is a k-bit string such that a represents x in binary representation, then the most significant bit of a is 1 if and only if x is greater than or equal to 2 to the power of k minus 1. This is exactly the threshold that we saw in the binary representation algorithm. The proof is quite trivial. If x is represented by a, then we can expand the number that a represents by the power series. We take the first coefficient, multiply it by its weight, and we're left with the remaining part of the string. Now we consider two cases. Either ak minus 1 is 0 or it's 1. If it's 0, then we know that x equals this part, and this part cannot be too big. It's bounded by 2 to the power of k minus 1 minus 1. If ak minus 1 is 1, then just this part alone equals 2 to the power of k minus 1, and this part is not negative, so x is greater than or equal to 2 to the power of k minus 1, and this completes the proof. Now suppose that we have an x within the right range, namely it is representable by k bits in binary representation, and we want to compute the binary string that represents the value x. Now, we have two options. Either x is less than 2 to the power of k minus 1, or x is greater than or equal to 2 to the power of k minus 1. If it's less than this threshold, then the previous claim tells us that the most significant bit is 0. This tells us, in fact, that x is in the range b sub k minus 1. Therefore, we can apply an inductive argument and argue that the k minus 1 bits of A from position k minus 2 to 0 are computed by the binary representation algorithm on the same x, but with a budget of k minus 1 bits. This is because x is now in b of k minus 1, as opposed to our original assumption that x was only in bk. Okay, so this is a smaller set. On the other hand, if x is big, at least the threshold 2 to the power of k minus 1, then our claim tells us that the most significant bit of A should be 1. Okay, now we know that originally x is not too big because it's in bk, so x is less than or equal to 2 to the k minus 1. That means that if we subtract 2 to the power of k minus 1 from both sides, we get that x minus 2 to the k minus 1 is less than or equal to 2 to the power of k minus 1 minus 1. Now, this means that the left-hand side over here is in bk minus 1. Okay, so this bit, the most significant bit of A, contributes 2 to the power of k minus 1 towards the representation of x. And therefore, we are left with the task of finding the binary representation of x minus 2 to the power of k minus 1 with a budget of k minus 1 bits. And this will be the bits of A from position k minus 2 to 0. So this is an alternative proof of the correctness of the binary representation algorithm. Okay, another way of explaining what the algorithm does is by using this rooted tree. So we have a root, and in fact, what I did here is I took the reverse of a rooted tree, because I directed the edges from the root to its children, okay? So up to this reversal of the edges, this is a rooted tree. This type of tree is often called a trie. Okay, and you notice that in this trie, the edges are labeled 0 and 1. Okay, now the leaves, I denote them by 0, 1, 2, 3. I label the leaves, and I made sure that they label the leaves in a correct fashion. Namely, if I look at a path from the root to a leaf, for example, the path from the root to 3, the labels along this path are 0, 1, 1. 0, 1, 1. This is the 0, this is the 1, this is the 1. Now, the number that is represented by 0, 1, 1 equals 3, which is the label here on the leaf. So I made sure that every path is labeled by bits that represent the number that is written in the leaf. So now, in order to find the binary representation of x, all I need to do is find a path from the root to the leaf that is labeled by x, as I did here. I went from the root and went to the leaf whose label is 3. Now, I labeled the edges of this rooted tree such that the edge labels along a path from the root to the leaf represent the value which appears in the leaf. Okay? So, what the binary representation algorithm does, in fact, it starts with an x over here, and it traverses this rooted tree until it reaches the leaf labeled by x. The bits along this path are the binary representation of x. Okay, so now what the algorithm does is it needs to decide, given when it starts in the root, it needs to decide if it goes to the left or if it goes to the right. If it follows the edge which is labeled 0, or does it follow the edge which is labeled 1? And the decision to follow the edge labeled 1 is according to the following rule. you follow the edge labeled 1 if and only if x is greater than or equal to 2 to the power of k minus 1. Okay, so here k was 3, x was 3, 2 to the power of 3 minus 1 is 2 to the 2, which is 4. So 3 is less than 4, and therefore we went along the edge labeled 0. Now, once we reach this node, we update the k. The k is decreased by 1. Okay, so now we're comparing 3 with 2. Therefore, we follow the edge labeled 1. But once we follow the edge labeled 1, we have to decrease x, because this 1 already contributes towards the representation of x. It contributes the value 2. So we subtract 2 from 3, so we get 1. And we ask, is 1 greater than or equal to 1? And the answer is yes, and therefore we follow the edge labeled 1. Okay, so you can think of this algorithm as if it extracts the bits of the binary representation from the most significant bit to the least significant bit. You may ask, what about finding the path from the leaf to the root? Let's start at the 3 and go up to the root instead of starting at the root and go down to the leaf. Namely, how can we extract the bits of the binary representation of x from the least significant bit to the most significant bit? Details of such an algorithm appear in the book. Thank you. Okay. How many bits do we need in order to represent the value x? So every positive integer x has a binary representation using k bits if k is greater than log base 2 of x. Why is this true? Well, look at our algorithm. The algorithm succeeds provided that x is less than 2 to the k. So we just take the log from both sides, so we get log of x is less than log of 2 to the power of k, but log of 2 to the power of k is exactly k. We want to prove now the second question that we discussed, and that question is that every number in the range 0 to 2 to the power of k minus 1 has a unique binary representation. So for this purpose, let us consider the function which is defined by these triangular brackets applied to binary strings of length k. For every such binary string, it assigns a value between 0 and 2 to the k minus 1. This is something that we have already seen. Okay, so this is a function that gets as a parameter a binary string of length k and outputs the sum of this power series. Now we know that the range of the function is indeed between 0 and 2 to the k minus 1. We claim that this function is a bijection, namely it is both 1 to 1 and onto. What does this mean? It means that given a number, there's only one binary string that represents it. Therefore, representation is unique. Okay, how do we prove that it's a bijection? Okay. First of all, we know that this function is onto. The reason it is onto is because we proved that if x is in this range, then we can execute the binary representation algorithm with x and k to obtain a binary string consisting of k bits that represents in binary representation the value x. Therefore, this function is onto. Now, the domain contains 2 to the power of k elements. The range also contains 2 to the power of k elements, namely the cardinalities of the domain and the range are equal. And we have a function which is onto. We claim that this implies that the function is 1 to 1. So here we relied on an exercise that states that if we have a function from a to b that is onto, and if the cardinality of a equals the cardinality of b, then f is 1 to 1. Okay? This exercise can be proved using similar tools, to the tools we use in order to compare cardinalities using one-to-one and onto algorithms. Finally, I want to discuss the effect of shifting. What is shifting? Okay, we claim that when a natural number is multiplied by 2, its binary representation is shifted to the left, while a single zero bit is padded from the right. Okay? Let us try to explain what we are saying here. Suppose I'm looking at the binary string 0, 1. And I ask, what is the number that this string represents? It represents the number 2. Now, let's shift things to the left by 1. I concatenate it with a 0. What is the number that I get now? This number is 4. So, by shifting the binary string to the left and padding a 0, I took the number which I represented and I multiplied it by 2 to get a 4. Here's another more detailed example. I take the binary string 1, 0, 0, 0, 3 zeros. Now, I said that shifting to the left multiplies by 2. So, this is the shifting to the left of the string 1, 0, 0. But 1, 0, 0 is the shifting of the left of the string 1, 0. So I have a 2 from here and another 2, and I get 2 to the power of 2. But 1, 0 is a shifting to the left of the string 1. So I have here 2 to the power of 2 and another 2 because of the shifting, so I get here 2 to the power of 3, and indeed this all equals 8. What does the lemma say? The lemma says that if I have a string A, which is a k-bit string, and it represents the number lowercase a, and B is obtained by A by shifting A to the left by 1 position and padding a 0, then the number that B represents in binary representation is twice the number that A represents. Let's prove it. What is the number that B represents? By definition, it is this power series. I goes from 0 to k, bi times 2 to the power of I. Now, b0 is 0. And now I take the summation from 1 to k. But what is bi when I go from 1 to k? It is ai minus 1. Now what I do is I do a change of variables. I change the I to j. Sorry, I change the I minus 1 to j, and therefore the range goes from 0 to k minus 1. ai minus 1 becomes aj, and 2 to the power of I becomes 2 to the power of j times 2. Now this power series, is the number that is represented by A. So I get that the number that is represented by B is 2 times the number that is represented by A. And that completes the proof and also the chapter. Thank you.